Welcome back to Carneades.org. Today we're going to be continuing with our series, Dumbfounding Definitions, Dizzying Distinctions, and Diabolical Doctrines, a series sorting through some of the jargon of philosophy. In this video, we're going to be taking a look at what is the harmony of the spheres. Now, the harmony of the spheres, also called the music of the spheres, Musica Universalis, was an attempt to link up music, mathematics, and cosmology, which started with the ancient Greek Pythagoreans, but continued on through the works of Johannes Kepler. Basically, these thinkers claimed the planets of the solar system make an imperceptible music that harmonizes together because the ratios of their speeds correspond to consonant intervals in music. While this theory has been debunked, as objects don't make noise in a vacuum, it did lead to some interesting discoveries in cosmology and music. Let's take a look. So, the story of the harmony of the spheres starts with the Pythagoreans. Pythagoreanism is a pre-Socratic philosophy, which is in many ways a proto-philosophy. It had elements of philosophy, but also elements of a religion or a cult. Check out our video on Pythagoreanism for more. Pythagoreans held a range of views on metaphysics, mathematics, and the natural world. Much of their writing has been lost to time, or is confused by later Neo-Pythagoreans who wanted to hold up Pythagoras as the founder of philosophy. Pythagoreans held numbers in high esteem and thought that they were key to understanding the universe. They were especially keen on integers and ratios, especially ratios of the first four integers. Those first four positive whole numbers were really important to the Pythagorean belief system. In fact, that tetractys was an important symbol of Pythagoreanism. It was a triangle made up of points, with the first row having 1 point, the second row having 2, the third row having 3, the fourth row having 4. This was said to represent any number of things. The first row was a single point, representing 0 dimensions and unity. The second row represented a straight line, the first dimension, and duality, the Pythagorean idea of limit and unlimited. Check out our video on Pythagoreanism for more on those. The third row represented the second dimension, also 3 points of the full triangle making a plane, as well as the idea of harmony of limit and unlimited together. The fourth row represented the third dimension, also the 3 corners and the central point, making a view of a tetrahedron from the top down. If you were to draw a line connecting the 3 corners with each other and each of those corners into this central point, it would look like a tetrahedron from the top down. As well as this fourth line representing the overall cosmos, beyond that singular harmony of limit and unlimited up to the whole cosmos. There were lots of things. They were also excited that all of these points then added up to 10, which of course is an important number. You can look at this tetractys from any different direction and you still get the same pyramid, and so on. Now, this obsession with the first 4 numbers led the Pythagoreans to look for features of the world that corresponded to these numbers. A key idea that the Pythagoreans claimed to have discovered was the importance of mathematics to music. Specifically, that by dividing a vibrating string in half, it would have a pleasing consonance with the full string, what we would call the same note but an octave up today. So if you take a string that's vibrating, it will create a note. If you cut that string perfectly in half and then vibrate only half of that string, you will get a very pleasing consonance, what's known as an octave, or for us, the same note but an octave higher. 2/3 of the same string creates what's known as a perfect fifth, another pleasing consonant. You go to 3/4, that makes a fourth, yet another pleasing consonant. These ratios represented, of course, the 4 key numbers in Pythagorean thought, 1, 2, 3, and 4, being the octave, a ratio of 1 to 2, the fifth, a ratio of 2 to 3, and the fourth, a ratio of 3 to 4. Now, the Pythagoreans went on to create what's called Pythagorean tuning, which is based on the use of perfect fifths and octaves. The notes in a scale are created by moving up a perfect fifth, then when necessary, down an octave to bring the note back into the same range. The problem with Pythagorean tuning is that 12 perfect fifths should bring us back to our original note just 7 octaves higher. However, the math doesn't actually work out because 7 octaves and 12 fifths are not actually equivalent, though they are quite close. This dissonance that is created then between the note that should be the same, 7 octaves lower and 7 octaves higher, is called the Pythagorean comma, that missing bit that we've lost through all of these kind of transpositions. This is emblematic of the Pythagorean obsession with simpler numbers, as the Pythagorean comma means the tones get further from the harmonious patterns the further from the original tone you play. Modern music uses a more complex ratio, the 12th root of 2, to go between individual notes. This retains nearly identical ratios for the 4th and 5th, which are quite close to those perfectly pleasing consonances of Pythagorean tuning, but instead allows for equal spacing between each note and the octave to cycle perfectly every 12 notes, and so you don't get this creation of a Pythagorean comma where the dissonance increases the further out you get. The Pythagoreans would never have accepted this tuning schema, though, because it uses an irrational number, the square root of 2, something that the Pythagoreans strongly disagreed with. The story goes that the philosopher Hippasus, who discovered irrational numbers, was drowned at the sea by the gods because the gods hated irrational numbers, according to the Pythagoreans, at least. So, the key insight that the Pythagoreans had here, which was far ahead of their time, was that abstract mathematics could be used to describe the universe around us. They were very focused on the simplicity of numbers and ratios and argued that all numbers were rational, could be expressed as the ratio of two whole numbers. This means their solutions were limited, as they were disinclined to accept any irrational numbers or even complex decimals as universal constants, or things that could explain the world. They really wanted to explain the world in terms of these very basic ratios of numbers. They were convinced that this simplicity would override. Because they focused on the belief that the numbers governing the universe must be simple, in addition to the idea that mathematics could explain the universe, their solution set for explaining the world was limited. However, this underlying idea that mathematics, which was for many at the time considered a very abstract field completely divorced from reality, can be used to describe natural occurrences in the world and understand the world around us was a really important one, even if their application of it was overly simplistic due to their obsession with these basic ratios. We'll see more of this as we get into the harmony of the spheres. So this brings us to the spheres. There were several puzzles that the Pythagoreans were trying to solve. First, there was the issue of why objects that were observed on Earth that seemed to make noise when they moved very fast, but objects moving in the sky very quickly seemed to make no noise at all. You can think of swinging a flexible tube around and making a pitch of noise. The faster you move it, the higher pitch that noise gets. But when something moves very quickly through the air on Earth, it makes a noise. But these planets that seem to be moving very fast in order to be moving as fast as we saw them and yet be far away in the sky didn't make any noise at all. We couldn't hear them. Why was this? The ancients also observed that the pitch of the moving object was related to its speed. The faster it moved, the higher the pitch of that object. Second, the Pythagoreans wanted to use their theory of numbers to explain the movement of the heavens. Remember, they're trying to use these basic, simple ratios to explain natural phenomena that they found out in the world. They could use them to explain these features of tuning within musical instruments. They saw that the planets were moving at certain speeds in varying ratios. Given their focus on simple numbers, they calculated these ratios, and then they rounded them a bit to match with the ratios they'd found related to musical notes. This gave us the music of the spheres. The music of the spheres solves both of these problems. It claims that there is a cosmological music that is made by the spheres as they fly through the sky. They claimed that these spheres moved at speeds and distances from each other, which had the same ratios as the ratios they discovered for musical notes, of course matching their simple 1, 2, 3, 4 idea of the world, meaning that the sound from the heavens was not just a mindless cacophony, but rather a pleasing harmony that blended together based on these natural, abstract principles of mathematics. They explained The fact that we didn't hear this music was because the noise fades into the background when you hear it enough, like any noise. Since we have been hearing this cosmic music our entire lives, we don't notice it, but it is there in the background music of the cosmos. When you stare out into the night sky on a silent night, that feeling of awe you feel is listening to the music of the spheres. Now, of course, there are some issues with this theory. First, there's no sound in a vacuum, so the spheres are not actually making noise, despite moving very fast. Second, the Pythagoreans had a desire to oversimplify numbers, so they rounded off ratios that didn't quite fit with their picture of a simple world governed by small numbers. Once again, a good idea that mathematics can explain the world in interesting ways, not quite the amount of application or the depth of digging into the mathematics that would work for it. And some of this is bound by the feature of Pythagoreanism, that it was more almost a religious cult than it was a rigorous philosophical or quasi-scientific pursuit. They were interested in finding a story that fit with this belief that these basic simple numbers were the building blocks of the universe, and if there was something that wasn't quite on, then they would simply round that or tweak it to fit back into that belief. Third, there's the concern that even if pairs of these spheres would have made a pleasing consonance together, all of the planets playing their own notes at once would likely have resulted in a dissonant cacophony. Even if you could make the case that any pair of the spheres had a good ratio of their speeds to each other, why would all of them moving at the same time lead us to think that we would get any pleasing sound? So, no one really believes in the Pythagoreans' harmony of the spheres anymore, but it did prove the key insight that mathematics could be used to understand the real world, something we continue to use today. Philolaus, a Pythagorean, was arguably the first to put forward a model of the universe with the Earth as a planet which orbited around a central fire. In fact, this model became inspirational to Johannes Kepler, who refined the Pythagorean harmony of the spheres into his own version much later, back in the Renaissance. As with the Pythagoreans, this eventually proved to be incorrect, but it was another step on the path to apply abstract mathematics to the cosmos and did lead to many other important discoveries. So let's shift over to Kepler for a second. We're not going to delve into Kepler's theories in too great a depth, but here are some of the basics. Kepler posited that the distance between the orbits of the planets corresponded with the ratio of the distances between nested spheres inscribed in Platonic solids. Kepler, unlike the Pythagoreans, thought that numbers were a lower class of mathematical concept, below geometric ones. Geometric concepts were the true, interesting concepts that we should be paying attention to. We shouldn't be worrying about these basic integers, we should be caring about the Platonic solids. In other words, we have a sphere inside an octahedron, inside a sphere, inside an icosahedron, inside a sphere, inside a dodecahedron, inside a sphere, inside a tetrahedron, inside a sphere, inside a cube, inside a sphere. Each of those spheres corresponded to the approximate orbits of the planets. The smallest sphere corresponded to the size of Mercury's orbit, the next smallest to the orbit of Venus, etc., with the largest corresponding to the orbit of Saturn. According to Kepler, the number of Platonic solids proved that there were only 6 planets. Sorry, Pluto, and Uranus, and Neptune. Kepler proposed his own version of the cosmic harmony of the spheres. He argued that the planets created harmony that could be felt in the soul. This was a pure harmony, more akin to the harmonies of a mathematical proof than to sensible and audible harmonies of music. To understand how we can connect with and comprehend these abstract harmonies, Kepler argued for a version of Plato's anamnesis, the idea that we have innate knowledge that we remember from before we were born. Using slightly more complicated ratios and acknowledging a range of speeds and therefore notes with the planets, as opposed to a single constant speed, Kepler argued that the solar system was comprised of 2 basses, Saturn and Jupiter, 1 tenor, Mars, 2 altos, Earth and Venus, and 1 soprano, Mercury. Kepler argued that these sung in concordance at the beginning of time don't necessarily sing in concordance at all points in time, explaining some of the issues with the Pythagoreans, but might sing in a perfect concordance again at some point in the future. Now, as with the Pythagoreans, many parts of Kepler's philosophy didn't catch on. However, the underlying idea that mathematics can be applied to the planets led to substantial discoveries in astronomy, such as Kepler's laws about the elliptical orbit of the planets and the speed of the planets. Many still feel a sense of awe and harmony when looking out at the stars, though few think that they're actually making music. It is interesting, though, how these initial ideas about trying to draw connections between mathematics, music, and the stars led us to real discoveries about the motions of the planets. What do you think? Do the stars sing to you? Is the study of ancient theories of the cosmos informative on how they shaped our modern ideas, or useless, as most of them have been largely debunked? Leave your thoughts in the comments below. Watch this video and more here at Carneades.org, and stay skeptical, everybody.